All right, hello. Welcome to lecture 24. Today we're going to be talking about confidence intervals. Some announcements. So, as you guys know, the mid-semester feedback survey was due yesterday at 5 p.m. I'm very pleased to announce that we did get over 90% response rate, so you guys all get a point back on your midterm. Woohoo, yay. Yes?
When we saw our score yesterday, did I include the extra point or did I not?
So did the score yesterday include the point? No. So it's whatever point you got on Gradescope, and it'll be +1. Okay. That being said, the midterm grades are also released. Okay. So the midterm grades are released. They are available on Gradescope. If you did not get an email about it from Gradescope, please let me know ASAP, because that might mean your midterm was missing, which would be bad. Okay. So check Gradescope, check your scores, make sure you have your midterm there. Regrade requests will be open until Thursday midnight. Okay, so please, if you notice a discrepancy between what you put down and what our rubric says, please submit a regrade request on Gradescope by Thursday, and we'll take a look at that. A reminder that project 2, yes.
I just want to see my paper and all about mine.
Sorry?
If I just want to see my paper, like I don't want to regrade. I just want to see it.
Yeah, it's on Gradescope. So your test was scanned and put on Gradescope. Yeah. Okay. A reminder that project 2 is due on, so the checkpoint is due Friday, and the entire project is due Tuesday of next week. So get going on that. Finally, there is tutoring still happening this week. Let me finish this. There's still tutoring happening this week, so please sign up on the form on our class website or on Piazza. Yeah. Sorry?
Checkpoint is on correctness or completeness?
The checkpoint for project 2 is graded on completeness, as is the case for all checkpoints. Okay, so checkpoint is graded on completeness, but the whole project will be graded on correctness. It is quite long, in my opinion, so I suggest you get started as soon as possible. All right, let's keep going. So yesterday we talked about the bootstrap. Okay. The bootstrap was a method that we have for dealing with the fact that most of the time in real life, we only have one sample. Okay. Previously in the class, we had access to the population. So we had a population, and we can get more samples from the population. Now we don't have access to the population anymore. And then we said, OK, we think that the population looks like something. So for example, we think that the population gets about half heads and half tails in flips. But now we don't have access to even that anymore. So we don't have the population. We don't know what the population looks like. We can't get more samples from the population. So all we have is our one sample. And we have to draw some conclusions using that one sample that we have. The bootstrap is a way for us to do that. Because if we have a population, and we take a sample from the population, let's say we're estimating the median compensation, as we were doing yesterday, we can only get one median. Right? Our one sample gives us one median, and that's the end of the story. However, with the bootstrap, we can take our one sample and sample that to get more samples that look like they came from the population. That way we can get a sense of the variability of our estimate, the population median. Okay? The reason why it works intuitively is that if our sample is large and random, it probably looks like the population. Right? So this looks like this. And because the sample looks like the population, our resamples will also look like samples drawn from the population. And we can use our estimates that way. Yes?
Just to clarify this, when you're doing the resampling, are you taking smaller samples from the sample, or are you just reshuffling the sample like a permutation test?
Yeah, so the question is, what am I doing here in this resample? I'm about to get to that, but just to clarify here, when I take another sample from my sample, I have to sample with replacement. The reason is, if I'm trying to find that population, let's say I'm trying to find the median compensation. I have my one sample. Let's say my median compensation is like $10. Okay. Then if I just shuffle the rows around, my median compensation here will still be $10. The median compensation here will still be $10. So I don't get any sense of the variability of that population median. Okay. So I'm trying to get a sense of where could that, like how does that median compensation vary? Okay. Cool. Now, I introduced this yesterday, and a lot of you guys looked at me like I was crazy. And that's because this method seems like too good to be true, right? It seems like I'm making up data based on my sample. It seems like I can't do that. It turns out that you can. I won't go into the theoretical underpinnings of why this works. But if you're interested in knowing about why I can actually do this and why it's actually a valid thing to do, you can take more stats classes. Woohoo. Okay. So in this class, I'm only going to say that this works because all of these things look pretty similar. When we resample, we have to make sure that we draw at random with replacement as many values as the original sample contained. So if our original sample was 1,000 compensations, we need to draw from those. If our original sample, was 200 compensations, we need to draw from those another 200 with replacement. And that's because only by drawing the same size resample can we get an estimate that's directly comparable to the original. Okay? So if you're curious about how that works, you can try it out. So the code from today's lectures and this week's lectures are all available. What you can do is you can take that same code and just change some of the numbers there, right? So when you bootstrap, just change it to like 1 or change it to 10,000 or change it to whatever you want. Take a look at what kind of estimates you get and what happens if you try to go from there back to your population. Okay? You'll get something that's a little bit different. And that's because you need those sample sizes to be the same. Kevin?
So basically, it is like a permutation test almost, besides this with replacement. Right?
So Kevin's saying it's almost like a permutation test, but with replacement. I guess you could say that, although permutation implies shuffle. So it's not really a permutation test anymore because we're not doing permutations. So we're just pretending our sample is a population and taking samples from that. Yeah, Alex?
If you're taking samples from a sample and you're doing it with replacement, is the reason why you're doing it with replacement so you don't get the exact same sample?
That's right. So if I have my original sample of 200 and I sample another sample of 200, so I get a resample of size 200, but I sample without replacement, all I'm going to end up doing is taking my original sample and moving the rows around. It's going to be a random shuffle of my original. I won't get any variation in my estimate. Again, if you're curious, you can try it out. So it's pretty easy to change in the code. All you need to do is change the with replacement equals false, with replacement equals false, and then you can see for yourself what happens. All right, so let's do a demo. All right, so today's demo. Oh no, come on, there we go. But there is a cell here that takes a couple minutes to run. So what I'm going to do is I'm just going to run everything first and then go back and talk about what we're doing. Okay, so run that, run that, run that. All right, get that all started. OK, cool. So this should look familiar because this is the exact same data set we were looking at yesterday. This is a data set of every public employee in San Francisco, their organization, their job, and their total compensation, which was salary plus benefits combined. Okay, so we have this table. This is a population. This is our census, right? It contains every public worker. And our question was, okay, so here is a population distribution. So we can see that the median compensation for public workers in San Francisco was probably around like 100,000, somewhere in this range right here. Okay, so here it is, 107,000. And our question was, suppose we only had a sample. So if you only have a sample from the population, in this case, our sample size has changed. Yesterday, we were looking at sample sizes of 200. Today, we have samples of size 500. But in either case, we have a sample. We don't get to look at the entire table. So let's pretend for a minute that I didn't know this. I didn't know the actual population median. I only have this sample. Okay. What I'm going to do is I take that sample and I bootstrap it to get an estimation of those medians, right? So my one sample had a median of, it looks like in this case, the median for my one sample was around 102,000. I used the bootstrap, get more samples, get the medians of all my samples, and plot them on a histogram. What that gives me is I get to see the variation of my sample medians. Okay? So for example, here I have some samples that had medians of 997,000. Over here, I had some samples that had medians of like 110,000, right? And what we did yesterday was we said, OK, we have roughly the medians fall into this distribution. And we took the middle 95% of that. Okay, so I went over here and chopped off some guys here, chopped off some guys here, and said, OK, here is a range of our medians, median compensation. Right? That range has a special name. It's called a confidence interval. Okay, so it's called a confidence interval, but it's just for our purposes, it's basically just, OK, I think that my population median falls somewhere within this range. So I took my sample, bootstrapped it, got a bunch of medians. I think that my population median falls within this range right here, this yellow thing right here. And indeed, in this particular case, it does. So that population median, which was 107,000, does in fact fall within my interval here, my confidence interval. So in this case, we did a good job. Our population median did fall into that range. Any questions about this? Yes, Kevin?
So what is the exact definition of confidence interval?
What is the exact definition of a confidence interval? Basically, take my sample, bootstrap it, get a bunch of medians, take the middle 95% of those, and find like where the middle 95% lies. So here is like the left bound of my confidence interval. Here's the right bound, and that's my confidence interval. Okay. Yes.
So why do you find the median instead of mean?
Why do I find the median instead of the mean? What a great question. There's no reason. I just wanted to figure out the median, so I chose the median. Actually, the real reason, so there's like a kind of more subtle reason why we chose the median in this case. It's because traditional statistics methods, like the ones that you'll learn in a more traditional stats class that involve what are called parametric methods, that kind of stuff doesn't work on the median. So the median does not follow the same laws as the mean and like the standard deviation, all that stuff. So in this case, we chose a specific example because you can't do it with stuff you learn in the normal stats class, or at least an introductory stats class. Yeah.
So why should it always be the 95%?
Why should it always be 95? No reason. No reason. So I'm going to talk about what happens when we change that. Okay. But in this case, I just happen to choose the middle 95%. And in this case, the middle 95% does contain the population. Okay. So I wrote here a method just to do that whole thing. So this method called bootstrap median just says, give me a sample, give me the label of like what you want to bootstrap, how many times you want to repeat that bootstrapping process, and I'll just do the whole bootstrap for you. So here's like the for loop, here's a resample, all that stuff just in one method. I'm just going to be calling that method over and over again. So at this point in the class, basically, I'm not going to spend too much time talking about the code. Okay, not too much time talking about code because at this point, we're starting to begin talking about more conceptual stuff. So basically, you don't have to understand this right now, but you can go back to the lecture and take a look at it. You should be able to understand it if you read it. But I don't expect you to understand it in like the short amount of time we have during lecture today. Okay, so this method I'm going to use to bootstrap my medians. So yesterday, I left you with the question of, suppose I do this whole thing over and over again. So I go back to my population, grab another sample, make a confidence interval, grab another sample, make another confidence interval. Suppose I did it over and over again. Yesterday, if you happened to be here, you saw that I was unlucky enough that the population median didn't fall in my confidence interval like 3 out of 4 times. Okay, so that's pretty sad. That population median should appear in there a good amount of times because we have our sample looks at the population, so our resample should look like our sample. And so what I did here was all this code does is, and the reason why it runs so long is that it creates 100 confidence intervals. Okay, so go back to my population, grab a sample, confidence interval. Back to population, sample, confidence interval, and does that 100 times. So I can take from that 100 times, I can see how many times those intervals contain my population median. Okay, so I'm going to hide that. Can I hide that? Excellent. So I hide that. So I have here, okay, get rid of that. Darn it. No, it's already English. Stop it. Okay, so I have here a table of my intervals. Okay, so here's interval number 1, the left and right boundaries for the interval. Interval number 2. Okay, so I have here a bunch of intervals. And I want to find out how many of those contain my population median. Right? Let's take a look. So make that shorter. There we go. So what I want to do is I want to take only the intervals where the left boundary was below the population median, and where the right boundary was above the population median. So the left boundary is below, the right boundary is above, then the population median was in the middle. So I'm going to do that. Okay, so do that, where right bound is above the population median. Okay, so I have here, oops, forgot a parentheses. There. So I have here a table containing only the rows where my interval contains the population median. I can look at how many rows there are. So let's take however many rows are in here. So dot num rows. 98 of my intervals contain the population median. Okay, so that means I did a total of 100 intervals. 98 of them contain my population median. So we say, OK, that seems pretty good. 98% of the time, according to this simulation, we're going to get an interval that contains a population median. Now, I didn't ask you guys to run it. But if you guys had run this yourself and kind of waited with me for the whole thing to run, some of you would have gotten like 92. Some of you would have gotten like 97. Some of you would have gotten like 94. But the average number of intervals that contain the population median would have been 95. Okay? And that's related to the fact that we took the middle 95% of our medians. So we say that we have a 95% confidence interval because if we repeat that whole process, 95% of the time, our interval is going to contain the actual population median, the thing that we're looking for. So we have a pretty good chance of actually getting that population median in our confidence interval if we repeat that entire process. Okay. So what I can do now is, there's 98 there, but I can also show you visually where all these intervals came in. So here, the red line is a population median. And these yellow lines here, each one is a confidence interval. Okay, so here's one confidence interval. Here's another one. Here's another one. What you can see here is that almost all of them contain the population median, except for this guy, which was way out here. And let's see this one, which is like just a little bit off, but also off. Okay, so there are two of these guys that are missing, but looks like the rest of them did have the population median. Cool. So the reason why this is important is because with this confidence interval, we can do inference, right? So we have the slide which says why the bootstrap works. The only difference now is that we don't know what the population is. Okay? So suppose I did not know what the population was. I only had one sample. I couldn't go back to my population and get another sample. What I can do is if I construct that confidence interval, I can say I am 95% confident that my population median is within an interval. That gives me a range of values that I believe the population median is in. Okay, so if my interval was like 100,000 to 107,000, I would say, OK, population median is probably like in that range. If my interval was like 110,000 to 120,000, I'll say, OK, my population median is probably within that range. Okay, so that 95% confidence interval is estimating that parameter that we're trying to look at, right? So we're estimating the population median compensation. That interval says the population's median compensation is probably within that range. It's based on random sampling, and 95% is what we call the confidence level. Now, I had a great question, which was why 95%? Why not something else? And that percent can be any percent between 0 and 100%. Raising that percent higher means I have more confidence that my population median will be in that interval. However, if I raise that confidence, I'm going to get wider and wider intervals, right? As an example of like a trivial interval, I can just say it's not that hard to find a 100% confidence interval for this problem. I just say my confidence interval is $0 to like $1 billion, and that's 100%. I'm 100% confident that all the salaries lie within that range, right? So it's not really. So once I keep increasing it. Sure, like I get it. OK, for sure the population median is somewhere in there. But as I keep increasing it, I lose accuracy, right? I lose being able to say, OK, that this interval is small enough to actually let me make a judgment call. OK, so 95% is just arbitrary. You can adjust that how you want. But know that if you lower that number, there's less chance that your population median will be in that interval. If you raise that number, your intervals are going to get wider, and you're going to be less accurate. Okay, so there's a trade-off there. The confidence is in the process that generated the interval. So that entire process, population to sample to bootstraps to confidence interval, if you repeat that entire process a bunch of times, then we expect that our process here that we've shown will generate a good interval, or one that contains the population median 95% of the time. Okay. There's a caveat here, which if we say that this process generates a good interval 95% of the time, but that really means I have to go back to my population and grab a sample, like the whole thing. I can't leave out any steps in the whole thing. Population to sample to confidence interval. I can't just take my one sample and bootstrap that over and over again and hope to get good confidence intervals. If my original sample was way off, even if I bootstrap a bunch of times, my interval will still be way off. Okay? So bootstrapping does not make up for the fact that my sample was bad in the first place. It just says, on average, if I went back to if I took my most of the time. But a bad sample is bad. You can't fix that with bootstrapping. Any questions? All right, so let me show you a real example. And by a real example, I mean an example where I actually don't have the population. Okay, so here I have a table. This is a data set released by Kaiser. Okay. They had a study where they were wondering whether, so right here we have like newborn babies, and they had like the birth weight of that babies, how many days that baby was in the womb, how old the mother was, how tall, blah, 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 and whether or not that mother smoked. Okay, so whether or not that mother smoked, this mother did not, this mother didn't, this mother did. Okay. The mother smoking affected any of these attributes of the baby. So they wanted to take a look at that. Today we're going to ask a simpler question, and we're going to note that in this case, here are about 1,100 babies. Okay, so my data set contains about 1,100 babies, which is not all the babies, right? Is not all the babies that came from all the mothers. My population is somewhere out there, and if I wanted to actually get the population, I have to go back and interview and measure like all the babies from all the mothers. Can't do that because there's too many babies. Okay, so here's only 1,000 of those babies. We don't actually know what the population looks like. We have this one sample. Let's see if we can make some conclusions using this one sample. What I want to look at is, so here we have birth weight, and here we have the gestational days, how long the baby was in the womb. We can look at the ratio of weight to gestational days and try to see whether anything interesting is happening there. So let me take my babies, births, dot. Let me make that smaller, birth.show 3. Okay. Select out that birth weight and gestational days. Here's my babies table. Okay. I just had a birth weight, gestational days. What I'm going to do is create the ratio of weight divided by days. So let's do that. Call that a ratio of birth weight to gestational days. And take the baby's table, take the first column, divide by second. Okay, fix that. Here's my ratios. So we can see here that this baby had a ratio this much birth weight to gestational days. This one had 4.4. This one had 0.46-ish. So the basic idea here is, if the longer a baby is in the womb, the heavier it is when it comes out, and there's probably some like actual ratio of like how much I can expect that baby to weigh given how many days it was in the womb. Okay. What I'm going to do now is try to estimate what was the population ratio of like weight to gestational days. Okay. So going to take that, and let's look at this in the histogram, because we have some numbers here. We want to see what those numbers look like. Let's histogram them. Hist. So we can see that most of these ratios fall within like the 0.4 to 0.5 range, maybe a little bit below 0.4. Most of them are in this range right here. Okay. So this is my one sample. From one sample, I can see that my ratios fall within like this range right here, just about. All right? Let's try to find that median ratio. Median ratios.column. The median of this column right here. So it looks like the median in my sample, the median ratio of birth weight to gestational days was about 0.43. About 0.43, which means that if a baby's in the womb for, let's say, 100 days, I would expect the baby to weigh about 42 pounds, 200 days, like 84 pounds, etc., according to my one sample. Okay. So I believe these are in, I believe these are not in pounds. Probably way too much for a baby. I forget what units they are. I just realized 80-pound baby is a lot. Okay. So in either case, I'm going to take that ratio and bootstrap it. All right. So conveniently enough, I have this method called bootstrap median. I pass in my table, pass in which column I want to bootstrap. I want to bootstrap that thing 5,000 times. I can call it resampled medians. Okay, run that. Now what I can do is take the middle 95% of those medians. So done. The middle 95% means that I want to cut off 2.5% on the left side, 2.5% on the right side, because I want the middle 95%. So I want to take the 2.5th percentile and the 97.5th percentile. Oops, 0.97, 97.5. Let's see what that looks like. Okay, so in this histogram, I have 5,000 bootstrap samples. I've taken the median of each of those samples, and I've plotted them on a histogram. I've constructed my confidence interval, my 95% confidence interval for the population median, and it looks like this. Okay, so here is a really fancy-looking term, like fancy-looking phrase. I'll make you sound really smart. This is an approximate 95% bootstrap confidence interval for the population mean. You can say it to your friends, and they'll think that, wow, you know so much about statistics. But in reality, all we did was take our one sample, resample it, take the medians, find the middle 95% of those medians. That's pretty much what that confidence interval is. Is my confidence interval, and it is from 0.425 to 0.432. Okay, so we can say we're 95% confident that the actual population median ratio is somewhere within that range. Right? Any questions? Okay. Pause for water. Now, I mentioned before that if you were to run this over again, your confidence interval wouldn't really change. I can show you what happens. Okay, so I take this. So remember these two numbers. Let me just put them above. Take that, put it above here. Just so you remember what the previous value was. I'm going to run this again, but I'm not going back to my population and getting another sample. I'm just taking my one sample and bootstrapping it again. Okay, seeing if we get a different interval. 0.4255 to 0.4327. So that interval stays about the same, right? The interval stays about the same, which means that if my sample was bad in the first place, I'm pretty much always going to get a bad interval. So do note that this happens. I'm just going to leave this here. Okay, leave it there. Bam. So if I want to make an 80% confidence interval, that's not too hard either. So an 80% confidence interval means I want to shave off 10% on the left side, 10% on the right side, right, to add up to a total of 20% gone. So I'm going to just take that, put 10 there, put 90 there. There is an 80% confidence interval. It is smaller, right? You see how small that is compared to 90%. So bam, 90%. Here's 80%. But we're less confident that the population median lies within that range. Okay, excellent. So at this point, I'm going to take attendance. All right. So if you weren't here for my announcement, that link has changed. Okay. So it used to be @-d8. Now it is only @-d, because our previous form had some problems, and we made a new form. So @-d gets you to the new form. Give you a minute to do that. All right, so we have this nifty method called the bootstrap. Let's just take one sample and estimate something about a population from that one sample. All is well and good with the world. We can just bootstrap everything in sight. Unfortunately not. So there are some cases where the bootstrap does not work. And I want to make sure you guys know when a bootstrap will not work so you know when to do it. Okay? So the bootstrap will not give you good estimations in these particular cases. If I'm trying to estimate very high or very low percentiles like min and max, right, or even a 90th percentile or an 80th percentile of some set of numbers, if I try to estimate those percentiles, I'm not going to get good estimates because most of the sample, so the bootstrap depends on having a sample that's representative of my population. And if I'm looking for something in like a very high or very low percentile, that's going to be in the tails, typically in the tails of my distribution. That means that my one sample, like more often than not, will not have a good estimate for those things that are way off in the tail because there's higher chance that I just don't see those values. Okay? So in that case, a bootstrap will not give you a very accurate estimate. You don't want to do this. Okay? In fact, you just don't want to estimate any parameter that's greatly affected by rare elements of the population. So even if I'm trying to estimate the median, if my distribution was U-shaped, right? So if it looks like this, right? So I get a lot of values here, a lot of values here, but I don't really get the median of my distribution very often. Even in that case, I'm not going to get a good estimation of the median if I bootstrap it because it just doesn't appear very often. You want that what you're estimating to appear pretty often in your sample so you can bootstrap accurately. Yeah, Kevin?
Is there a term for like when a parameter is not greatly affected by real elements? Like, is that term like robust or what?
In this case, I guess the wording here is not super great. What I'm trying to say is any parameter that doesn't appear in the population that often. Okay, so robust, not exactly a term that we're looking for, because the median is considered like in the statistics, it's considered like a robust statistic. But in this case, even if I'm looking at the median, if my distribution is a U-shape, I'm going to have a bad time bootstrapping it. Okay, so it's just, you can't bootstrap stuff that doesn't appear very often. It needs to appear pretty often in order for Bootstrap to get that in the resampling. Okay, so if I bootstrap whatever I'm looking at, and that distribution of my statistic is not bell-shaped, okay, so we saw before, we looked at the median. Every time I bootstrapped, those medians came out in kind of a bell shape, right? Bootstrap the median, comes out in the bell shape. We plot those on a histogram. That's kind of symmetrical, bell shaped, pretty nice looking, right? If it is not bell shaped, like really like off in somewhere or another, then we're going to have, we can't really use that middle 95%, right? That 95% confidence interval there, the reason why we can shave off 2.5% on the left and 2.5% on the right is because we're assuming that the distribution is symmetrical. Right? So that's why we can shave off the same amount on the left and right side. If that distribution is something else, like something random, it's going to be harder to actually do that confidence interval. Okay, so what you want to do is you want to bootstrap and take a look at the distribution of your statistic. If it's not bell-shaped, you're gonna have a bad time bootstrapping. Finally, if your original sample is very small, like say, there's some rules of thumb here. It just depends on what you're studying, but typically a rule of thumb right here is like below 50 or so. If it's very small, or just to you, if it seems very small, the bootstrap will give you random results basically because your sample is too small to begin with. It won't give you a good and accurate estimate of the population parameter. All right. Any questions about these? Yeah.
How can we know our sample? Like you said, like if the sample in the beginning is like is a bad sample, like even if I do Bootstrap every time it will not give me a result. How can I know if my sample is good?
So Abdul Rahman asks, okay, so if I can't get a better interval by just bootstrapping the same sample over and over again, how can I actually get a good sample, or how do I know when my sample is bad? The truth is you don't. You just hope. If you increase your confidence, you increase your hope, but otherwise, you can't know. That's statistics. So there's no way for you of knowing whether or not your sample just happened to be really, really off in one direction or not. It works. But if your sample is large enough, you know that in the long run, you're going to win. You know that in the long run, your samples will come out nicely, and you're going to get good confidence intervals. Yeah. Okay. So this seems like a kind of random criteria. Basically, the rule of thumb here is if you did have, so you want your original sample to represent your population, right? So in some cases, so it's hard to say like exactly when to have a cutoff for when it represents and when it doesn't represent. What I would recommend you doing is, if you're looking at the case where you do have some population, you can take a sample and compare distribution to your population. Okay, so if you have the population distribution, which I just said you don't, but suppose you did, and you want to see what a good sample size is for the population, you want to plot that population and take a sample and then plot the sample distribution and take a look and see whether those two distributions are similar. And if they are, then you can bootstrap confidently. Okay. All right. So I have a discussion question for you. By our calculation, an approximate 95% confidence interval for the average age of the mothers in the population is 26.9 and 27.6 years. Okay. So let me show you that. So here it is. Okay. So I had a question which was, why not the mean? Why the median? Okay. And the truth is, you don't have to do the median. You can also do the mean. Let me show you how to do that. It's actually not too hard. I'm going to use a tried and true technique of copying and pasting. Okay, so here is my Bootstrap median method. Copy that. Here is the Bootstrap mean method. So there's the code. What I'm going to do there is just take out that. Whoa, what's happening there? Whoa, OK. Take out that. OK. Whoa, that's spazzing out. OK, so put that here. Wow, what is happening here? Try it. Interesting. OK. My for loop is like really doing something to itself. All right, so what I'm going to do here is I have the same code for the medians. I'm going to delete the minimum amounts of code to change this to Bootstrap mean, which means I'm going to go here and delete these two letters, and these two letters, and these two letters, and these two. All right, and then I'm done. So if I want to do the mean, it's not super hard. I just need to change my np.median to np.mean. Now I'm bootstrapping the mean instead of the median. Okay, I can pretty much do that with any statistic I want. Now again, you want to choose something that does show up in your sample pretty often, but the mean is fairly good because it's like right in the middle. Okay, so I'm doing the mean, and here's a method to bootstrap the mean. Here we go. And now I can just call that method over and over again. So here is a bootstrap of, let's do the maternal age, because that was a question. Take my births table, which looks like this. Birth.show, here we go. Let's bootstrap that maternal age column. Do that 5,000 times. Okay. And this just repeats the code that I have up above. So I've just copy and pasted that code down into this method. When it is done running, I should see a distribution of my sample means, along with a 95% confidence interval for those means. So it looks like here, my confidence interval is about 26.9 to 27.56. Okay? So how do I interpret that? Let me go back to my question. So my confidence interval was something around that, so 26.9 to 27.6. True or false? About 95% of the mothers in my population were between 26.9 and 27.6. Talk it over with your partner.
We're just 95% confident that the population mean inside whatever interval those estimates. We're just 95% confident. That's something to do with the fact that not 95%. We know that's not true. What it means is
OK, so show of hands. How many of you guys think true? Let's do true first. How many of you guys think false? OK, so basically everyone. And it is indeed false. Okay, why is it false? It's because our confidence interval is estimating the average age of our mothers, not the actual where the mothers fall themselves. Okay, so we're saying the average age of the mothers is probably within this range. So I can't say the actual mothers in my population were between these 2 years of age. To prove that to you, I can just look at my sample. So my sample, OK, close the form. If I look at my sample, so here are my births. If I histogram the maternal age, in my sample, I had a bunch of ages, right? So here are people 17 to 21. Here is 30 to 32, 35 to 37, right? And I can see that clearly the mothers are not within this 26 to 27-year-old range. They're actually all over the place. Okay, so again, the confidence interval is estimating a parameter. It's not estimating this actual distribution here. All I'm saying is, OK, in my population, the average maternal age is probably around 27 years of age. But it does not say, all my mothers are in this age range. Okay, so there'll be more questions for you on interpreting confidence intervals in homework 6, I believe, which is coming out next week. I hope you guys are very excited for that. Otherwise, I'll see you tomorrow.